All that?
All that.
What the fuck?
For $4.99.
We don't know how good the mic quality sounds. Hopefully it sounds fine.
I don't really do like a survey. I didn't know that actually worked.
It worked because they said like we answered and there's like a little sign that says $4.99 and it's for burgers, for fries. It's not bad now.
If things get in here, I might have to mute the microphone.
Dude, I'm switch. You switched your seat?
Yeah, I need to charge my laptop.
That's you! He showed up on
It's what I got for you, bro. It's Christmas came early, like 360 days.
Oh yeah, has to be good right now. No.
Damn.
You know cards?
Not much.
Somebody pick that up last.
Dude, that's bad.
I got you a camera and a mic for like.
Oh.
I know.
Oh, well, that would be good for the camera. I got
It's
you.
got a microphone.
Let's see how well this works.
My brother used to. Wait, really? When you're driving, it just shuts off? So my brother, when he had a Corvette, and I used to be in his car a lot, and whenever he turned left on like the highway, it literally stopped and just stopped every time. And I think there was something to do with
This doesn't have rotation. Sucks. Alright,
fuck, I can't remember.
Okay, you know, I'll just say it like this. No! Oh, it's fine.
Hi, Professor Elias. Good to see you.
He's muted.
Oh.
Good morning, guys.
We miss you, Professor Elias.
I miss you too. I really don't like it.
Sound fine?
Hopefully. 3 more weeks.
I don't know how good this sounds.
Okay. So you guys were able to fix the microphone in the classroom?
Yeah, I got one right here, and then someone brought in a camera as well.
Okay, thank you. Thanks a lot for your help, guys.
Oh, no. It's gonna
Okay, so as I told you, please put your questions on chat, and then we start. We still have 1 minute. So any questions you have from the homework, feel comfortable to put it on chat, and we go through them before we start.
You liked it? Yeah. Did you watch back this?
Okay.
Yeah, I watched it.
Yeah.
Like that entire
All right. I have one question. Any other questions? As I said before, please do the homework. There is no way out in this course without doing the homework. It is, as you guys know, the hardest calculus course. But if you do the work, you will be okay. If you don't, you will not be okay.
I just moved. I've had no network for the past few days.
Okay.
Should be up to
All right. So it's 10 o'clock. We start. So I will answer Caitlin questions. So it's part K in problem number 6, I imagine. So we have the following integral. Integral of cosine 2t divided by 1 plus 6 sine 2t. dt. And the question is, of course, to evaluate this indefinite integral. As I said several times, in those integral, we have to really to look carefully, stare at the integrand, what's inside here, and see what's really the best approach for it. So what do you see in this integral? Is there any relationship between what's going on inside in here?
Yes.
So what do you think I want to do? Okay, ideas?
Could you split up the cosine of 2t to be multiplied by 1 over 1 plus 6 sine 2t?
Yeah, I can do that. And what's the goal behind it?
to get it to where you could get 1 over u. So you could replace 1 plus 6 sine 2t to be u.
Okay, all right. So the main idea is your classmate said, I mean, that's really the bottom line. We look at the denominator and we look really at this piece of the denominator right here. And we should notice that the derivative of sine 2t is actually up to a constant cosine 2t. So basically, the derivative of the denominator is almost the numerator up to a constant. So in this scenario, as your classmate said, the wisest thing to do is to set the denominator to be my u. So my denominator will be my u. And now I proceed verbatim. I evaluate the derivative, which is equal to the derivative of 1, it's 0 plus 6 times the derivative of sine 2t, that's again the chain rule, the derivative of the outside, which is the sine, it's the cosine 2t times the derivative of the inside, which is 2. So now I multiply symbolically by dt. This will give me 12 cosine 2t dt. Now at this stage, I stop here. I go back to my integral and I substitute everything in terms of u. And now I will do what your classmate suggested. He told me you can rewrite this as the following. Sine 2t. And now the substitution become actually very clear. So this will become equal to verbatim. This piece here, this would be your 1 over u. Done with that. Everything in terms of u. This piece here, cosine 2t dt, I already saw it. This is my other I, which is I have to keep it on that. And yeah. So we have to pull it from here. That's what I have, cosine 2t dt. So I need to divide by 12 both sides to pick up the cosine 2t. So from here, I have 1 over 12 equal cosine 2t dt. So cosine 2t dt will become 1 over 12 du. So now I have a very simple integral in u, and now I proceed. 1 over 12 is a constant. Constant, we are allowed to get them out of the integral. 1 over u du. Very simple integral in u. Now I evaluate this completely as integral in u. I forget about xt for a little bit. So this is the natural log of u. Now that I evaluated that, finally, I will substitute, go back to my original variable, and I put it back. Plus. Okay. All right. Any other questions from the homework? Please, I repeat over and over, you have to do them.
Could you
Any
go
other
over
questions?
Could you go over Q real quick?
Q?
Yes.
Sure.
Thank you.
So Q is the following. So we're doing Q from homework number 6. We have the integral of x times to the power 11 dx. And the inside is 3x plus 1. And as I said yesterday in class, there are, a special kind of substitution that I usually help you at the beginning to do them. So, of course, none of us is going to take 3x plus 1 to the power 11 and expand it. This is absolutely impossible. So we're going to put u to be the 3x plus 1. And the same thing, we evaluate the derivative, which the derivative of 3x is 3, and we multiply formally by dx. Now we stop and we go back to the integral, and now we need to substitute. And that's really what the problem is, because we have an x, which is not the derivative of the inside, but still this problem would work. Okay, everything in terms of u. So now I'm stuck with x. I have to substitute it in terms of u. So I go back here and I solve for it. So x is going to be u minus 1 divided by 3. So instead of x now, I have, if you want, 1/3 u minus 1 times 3x plus 1 is my u to the power 11. Everything in terms of u, as you realize. And my dx, okay, I look here, I don't have quite dx. I have to solve for dx. So I divide by 3 both times, and I solve for my x. So that's going to give me 1/3 du. This is now an easy integral in u. 1/3, and I'm multiplying here. So I multiply 1/3 by 1/3, which will give me the 1/9. A constant, I can take it out. Now, obviously, I have to distribute. That's the only way out. I will have u to the 12 minus u to the power 11 du. Very easy integral in u. Nothing really is left for us. So this will end up being 1/9 times u to the 12 would be 1/13, u to the power 13. U to the 11 is 1/12 u to the 12. I'm done. Now I go back to my original variable because that's an integral in x. So that's my variable is x. My answer has to be also in x because I'm looking for the function whose derivative is what's inside. So I cannot keep u. That's an indefinite integral to the power 13 plus c. So this will give me 3x plus 1. And this will give me 3x plus 1. Okay? Questions before we move on? All right. Again, I repeat myself over and over. Make sure you do every single one of them. And if you can't, you can ask me in class or come to my office hours. Don't not fall behind. All right, so today we are going to review. So the second review I want to make from Calculus 1 is definite integral. And once we're done with that, we can start the new material. So review 2 is definite integral. So let us remember indefinite integral. Indefinite integral is a function, nothing more than a function. When you differentiate it, you get f of x. So that's an indefinite integral. So it's really a function. Now we're going to talk about something called the definite integral. Definite integral. To talk about definite integral, I have to talk first about what we call Riemann sums. So I cannot talk about definite integral if I don't talk about Riemann sums. So first, I remind you the definition of it, and then we do an example just to refresh your memory. In Calculus 1, we talk about right Riemann sum, left Riemann sum, midpoint sum. In this class, I don't want to go over all of them, so I will only talk about right Riemann sum. The others are fairly similar because that's really what I need is the idea of a sum more than right, left, or midpoint. So most of my example will be basically right Riemann sum just to simplify the presentation. So we have a function f of x. Of x be a function which defined on an interval ab. I have this function. So graphically, that's my function. So this is my a. It doesn't have to be increasing. I'm just making the picture clear, easy. So that's my interval ab, and that's the graph of the function. So what is the right Riemann sum? We take, so right Riemann sum, with n subdivision. With n subdivisions. With n subdivision. All right. So what this means? So we take the interval AB and we divide AB into n equal subintervals. So we take AB and we split it, equal subintervals. So we take this and we split it into little pieces, n of them. Right? And we let delta x to be the length of each subinterval. Okay, so delta x for us is, we divided delta x is from here to here. That's my delta x, it's the length. It's from here to here. That's the delta x, this little bit. That's the delta x. So delta x is usually equal to what? Do you guys remember? If I take the interval AB, split it into n pieces, what is the length of every piece? Anybody remember the length? Anyone? Go ahead, say it. I don't care what the answer is. What did you say? I couldn't hear you.
B minus A over N.
Right, because from here to here, it's B minus A. That's the length from here to here. If you divide it into n little pieces, then the length of every one, so you're taking a length of B minus A and you divide it by n. Okay, so that's the length of every piece. Now the end point of those subintervals, we are giving them name, letters. So we're gonna call this x0. This one will be called x1, x2, and so on. This will be called xn. Okay, and an arbitrary one, it means somewhere in the middle, like we can call this xi, the one next to it, xi plus 1. So we're going to give names to the endpoint of the interval. And now let us recall what the right Riemann sum is. So the right Riemann sum is defined as follows. So you try to remember from last semester how we defined it. The right Riemann sum, which is we denote it by R for Riemann, N for the number of subdivision, is defined as follows. Can you guys remember how we defined it? Always try to concentrate so you guys can recall all the info from the previous. So we defined it as, we took the value of the function at x1, f of x1, and we multiply it by the little delta x. So it was the value of the function at x1 times the delta x, where the delta x is changing with the number of subdivision. It's b minus a over n. Plus, we kept doing the same thing. It's the value of the function at x2 times the delta x. Plus, we kept doing the same thing over and over. And the last term is the value of the function at xn times the delta x, which is graphically, you take the function f, you take the output at xn, and you multiply it by this little bit of delta x. And in sigma notation, we introduce the sigma notation. So this is the sum. Instead of writing plus, 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 it's the sum of. What's changing here in the sum is the subscript of x. That's what's changing. So it's going to be sigma f of xi times the delta x, where my I is from 1 all the way to n. Or And I usually like you to be able to see both of them. The second writing emphasizes that the delta x is not fixed, depend on the number of subdivision, or this is f of xi times b minus a over n. So that's the Riemann sum that it has somehow to stick to your mind all the time. So you have to recognize a sum like this as a Riemann sum. Let's take a very simple example before we go back to the definition of the definite integral. So very straightforward example. Let me start it in a new page. So example. Okay. So I take the function, let f of x equal x squared. Very easy function. Okay, and the first question is, find the Riemann sum with n subdivision. So find the Riemann sum with n equal to 4. It means with 4 subdivision on the interval 1, 3. Okay, I have no intention of doing a lot of subdivisions. So always we graph the function so we know exactly what we're doing. F of x equal x squared, so that's nothing more than a simple parabola. I want it on 1, 3, so so this is my 1 here, and this is my 3 up here. Okay, so that's my function. And so first, n subdivision, it means I have to divide this into 4 equal pieces. So this is 4 equal pieces. So these are my pieces. So if delta x here is the length of every piece. So it's 3 minus 1 divided by 4. My delta x is a half. It means this little thing here, this is the delta x. So if this is 1/2, so those points are going to be 3 halves, 2, 5 halves, and 3. So let us evaluate simply the Riemann sum. So it's the value of the function at 3 half times a half plus. So f of 3 half, that's the value of the function here, times the delta x. All right, let us remember, what does this represent geometrically? Times a half. Geometrically, what does it represent? Go ahead. So f of 3 half, it's the length from here to here. We are multiplying it by a half. So this is going to be the area of this rectangle, of the rectangle. Okay, that's what the first term is. We add to it the value of the function at 2 times a half, which is going to give me the area of that rectangle. We add to it the value of the function at 5 halves times a half, which would give me the area of that rectangle. And finally, the value of the function at 3 times a half, which give me the area of that rectangle. So that's the Riemann sum. And now we substitute. Of course, f of 3 half is 3 half squared multiplied by a half. F of 2 is 4 times a half. And we can do all those computations. And we get 10.75. So that's going to be R4. And geometrically, based on this picture, geometrically, R4 is the sum of the area of the rectangle. Sum of the area of the rectangle. So this is how we evaluate simply R4. Now, suppose I ask you to find the B. Suppose my question is evaluate Rn for n equal, let us say 100, 1,000, 2,000. Now, of course, you cannot be doing that. I have the answers for you, but the idea is to make the point. So what do I mean by that? If n equal 100, so I want to evaluate this, it means the delta x in this case is very tiny. It's 2 over 100. And Rn, basically we do exactly what I did for R4, but we're dividing it into 100 pieces. So what we are doing here is we're covering this with very, very tiny little rectangle. Very, very tiny one. And as you remember, and the idea is basically to find the area under the graph of this function. That's really what it is. So, okay, we can find R100. And we're gonna get 8.74. That's if we evaluate it. And equal 1,000, we can do that. And now the delta x is very, very, very tiny. That's the whole idea. So we're covering the region with very, very thin rectangle, as thin as your imagination can go. And this, I get R1000 is 8.67. I can keep going, 2,000. My delta x is also tinier. And R2000 is 8.67. So this is going to be 47 and 07. We keep doing this. And then what do we realize? When the number of subdivision, n becomes very large, so when n is basically going to infinity, as the number of subdivisions belong to infinity, those Rn are almost equal 8.67. So all those Riemann sums obviously are becoming close to this number, 8.67. This number is what we call the definite integral. So 8.67, this is what we called, this is called the definite integral of f on the interval 1, 3. So the definite integral is basically what's happening to those Riemann sums, because as the example shows you, when we take more and more subdivisions, the value are becoming closer and closer to each other. The number that I get close to is called the definite integral of f on the interval 0, 1, and that's what we denote by integral from 1 to 3 of x squared dx. And geometrically, at least in this particular example, geometrically, this number 8.67 is the area under the graph from 1 to 3. So this point 8.7 is the area under the graph. So that's really the idea of definite integral that I'm going to define more formally in a second, which is you take those sums and you start evaluating them for larger and larger number of subdivisions. You realize that all the Riemann become close to a fixed number. This fixed number is the definite integral. And it geometrically represents the area under the graph because that's what the Riemann sums represent. So formal definition of Riemann sum. Formal definition of definite integral. So definition of definite integral. So the definite integral. So you have a function f. The definite integral of f. Definite integral of f on the interval AB, denoted by integral from A to B of f of x dx is defined by the integral is. So that's our definition. I mean, that's the definition. You take those Riemann sum, the one that we're talking about. So f of xi, delta x, I equal 1 to n. So you evaluate the Riemann sum for larger and larger value of n. And the definite integral is what's happening to those sums when n goes to infinity. Okay, so that's what's the definition of the definite integral. Or I always write this sum two ways. The second way of writing is to emphasize the fact that delta x is changing with the number of subdivision. But I want you to be able to see it both ways. I equal 1 to n f of xi times b minus a over n. So the definite integral is intuitively nothing more than those sums when n is large. So that's how we view the definite integral. Means we take the interval AB, split it into pieces, and evaluate those sums. The larger the n, the better it is the approximation to definite integral. So it's really basically those Riemann sum when n is very large. And now let us recall the reason for the notation. Remember we've talked, of course, everybody's professor in 163 talked about the reason for the notation. So let us recall, let's a few minutes spend on the notation. So A to B, f of x dx. Okay. A and B, A, B are called lower limit and upper limit. And those tells you what interval you're gonna divide into pieces to evaluate the Riemann sum. So this is tell you about the interval you have to divide. So those are called lower and upper limit. That's the interval you divide. That's crucial. And upper limit. Now, this wiggly thing, do you guys remember it stood for what? Represent what in this whole picture? Anybody remember? Sum, exactly. It's the letter S, which stands for sum, that you take the letter S and you stretch it. You get this symbol. And this represents the idea that we're taking the sum of things. That's where this notation comes from. F of x dx is telling you you're taking the sum of what? You're taking the sum of f of xi times delta x. So this notation is totally, fully inspired by the process, by what this integral means. So you're adding quantity of the four f of xi times delta x. And that's really where the notation is coming from. A and B is crucial. They're telling you which interval you are dividing into pieces and evaluating the sum over it. So that's really the reason for this notation. Okay, now let us go back and talk one more time about geometrically what this integral means. And the goal of the first part of the course is actually to broaden our understanding of the definite integral and use it for a lot of other applications. But for now, we are sticking to the idea of area for a little bit. So one more time, I go back to the geometric interpretation of the integral because it's simple. important, not simple, sorry. So geometric interpretation of the integral. Geometric interpretation of the definite integral. We will divide this into two scenarios. For the first scenario is case 1, the scenario where my function f is absolutely positive on the interval AB. It means the function is above the x-axis, it doesn't take negative value. So this is very much like the picture, like f of x equal x squared. That's really the picture I have in mind. So that is the function. That's a and b. Okay. In this scenario, the integral the integral is the limit of those Riemann sum. And every Riemann sum represents the sum of the area of those rectangles. That's really what the sum represents. So the integral is going to be the area under the graph. So the area of this, that will be the integral. Because the Riemann sum represents the sum of the area of the rectangle. When n is very large, we're getting the area of the rectangle. So if the function is positive, it's the area of the region bounded by the graph of f, the x-axis, and the lines x equal a, x equal b. So I read it and I explain verbatim what I'm saying. It's the area of the region which is bounded by the graph of the function, that's the graph, the x-axis, that's the x-axis, the lines x equal to a, that's the line x equal to a, and the line x equal to b. That's the area. So as long as the function is positive, that's what it means. Case number 2. What if the function start taking positive and negative value? What does the integral represent? Okay. Right, I move on. So f of x takes, so case 2. F of x takes positive and negative value. So do you guys remember what does it represent in this case?
It represents like negative area, or like let's say you were like moving somewhere, it would represent like you moving back from the origin or something like that.
We don't move it. Try to remember. You're half correct. I don't know what you mean by move it though.
I don't know either.
Okay, all right, so let us remember. F of x takes positive and negative values. To understand the definite integral, we have to understand what the Riemann sum represent, because the definite integral is nothing more than what happened to those Riemann sums. So if f is positive, the Riemann sum is the sum of the area of those rectangles. It's very easy. Now, what do the Riemann sum represent when the function takes positive and negative value? So let us remember this picture now. So I'm going to draw a Riemann sum. So my function here is going to be positive, negative, positive. So I'm switching these. So negative a, and right here, that's my b. Okay, so I'm going to analyze. So first, let us analyze the Riemann sum, because that's how we can understand the definite integral. Okay, analyze the Riemann sum. All right, so I will not take a lot of subdivisions because it will blur the concept. So I'm going to take 6 subdivisions to make our life very easy. Okay, so I'm going to call this x1, x2, x3, x4, x5, and x6. So what is the Riemann sum? It's the value. So now I'm going to copy it verbatim, and then we'll analyze the meaning. The value at x1 times the delta x plus the value at x2 times delta x. I know that that's boring. The value at x3 times delta x. That's why I took very few subdivisions. And then when the function is positive, x4 delta x, x5 delta x, and x6 delta x. So that's my Riemann sum. All right, let's see the piece that's easy to interpret. This piece, this is where f is positive. Here, f is positive. Okay, when I take f of x4 times delta x, I'm going to get the area of this piece. That's what f of x4 represents. If I take f of xi times delta x, this is going to represent the area of that piece. This is where the function is positive. I don't really have any issue. When x6, the function is positive, so we're going to get the area of that piece. So when the function is positive, this will represent the sum of the area of those rectangles. So let me mark them in red, so I can talk about red rectangle versus other color. All right? Now, what happens when the function is negative? So this piece here, this is f is negative here. When I take f of x1, I get a negative number right here. And I multiply it by this little bit, the delta x. So question number 1, f of x1 times delta x, is it going to be a positive or a negative number? It's definitely going to be negative number because the value of the function is negative. But what is it going to represent? So it's definitely not the area because the area is a positive number. What this is going to be representing is minus the area of the rectangle. It will not represent the area because it's a negative number. It's going to be minus the area of that. So let me explain it in numbers. So that's the situation. So if you have, so this is my function, wherever I drew it. So this is f of x1. I don't have to write, but I want to make sure you understand this. Suppose by just argument that f of x1 is, let us say, a minus 2. It's negative number. It means the length here is 2. That's the length. Means when I take f of x1 times delta x, I'm getting the value, which is minus 2 times delta x. So this piece, the 2 times delta x is the area, but then I will get minus the area. That's really what it happened. So when f of x negative, f of x1 times delta x is giving me minus the area of this rectangle. F of x2 times delta x will give me minus the area of that rectangle. F of x3 happen to be 0, then it just gives me a 0. So this piece here, this piece of the Riemann sum will give me minus, so I'm going to take minus the area of that, plus minus the area of that, plus minus the area if I had more subdivision. So it's going to give me minus the sum of the area of rectangle below the x-axis. Give me minus those. Now, when the function is positive, I will get plus. This piece here is the sum of the area of rectangle above the x-axis. So that's really what the Riemann sum represent. Understanding the definite integral, we have first to understand what those Riemann sum represent. So for positive function, I don't have any issue, it's the area. For negative and positive, it's slightly different. So now, when the number of subdivision goes to infinity, what is going to be the integral? What does the integral going to represent? So when n goes to infinity, it means we're starting to take more and more subdivision, more and more, more and more, more and more. That's really what's happening when n goes to infinity. So when n goes to infinity, what does the integral going to present? It's going to be equal to. So this is the picture now. This is my A, and this is my B. Okay. So the integral is going to represent. So I have two regions, that region in black and this region in green. So I'm going to call this region, let me call this region S, and let me call this region D. So the integral is going to be minus the area of the region below the x-axis. So the contribution of the piece below the x-axis is minus this area plus the area of the region above the x-axis. And this is basically because that's what the Riemann sum represent, their limit is going to represent the same idea. But this time, instead of taking sum of the area of rectangles, it's the area of the whole region, because we're taking very, very thin rectangle, which is covering the region. All right, so, and this is called net area. The book used the word net area for this region. So the net area means minus the area of the region below plus the area of the region above the x-axis. Okay. Any questions? Okay, is it making sense now? We don't move anything. It's just, that's what it is. All right, so let us make a one more quick example along the same line. So now I would like it, we will do the following example. I would like to do two examples. The first example is just to make sure we understand the we're going to take the graph of a function. So let f be the graph of the following function. And the function is like this. It's a straight line. That's my function. Minus 2. Let me call this point 2. And this point, let me give it 6, 4. So this is f4. Okay, so that's the function f of x. Okay, so the question here is to use the geometric interpretation, nothing more, nothing less. And the question is use the geometric interpretation of the integral to evaluate the following. Integral from 0 to 2 of f of x dx. Use pure geometry. All right, I want answer from you. So 0 to 2. 0 to, it means I'm looking at this interval. That's what 0 to 2 means. And this is my function f. And the question is, what's the definite integral using the geometric interpretation? Anybody can give me the answer.
You can use a triangle formula.
We use a triangle. We're going to look at the area of this triangle. The area is a half, that's area, times height times 2, times 2. It means the area is 2. However, what's the value of the integral? Quickly. What's the value of the integral? Is it 2?
No.
It's -2?
Absolutely negative 2. Okay, the function here lies below the x-axis. So here, let us note, f of x is positive. Sorry, f of x is negative on the interval 0, 2. Absolutely negative. So the integral is minus the area because the Riemann sum, when we take them, will give me minus the area. Okay, that's what I mean by geometric interpretation. Now, part 2 is, what's the integral from 0? Sorry, this is 6, my apology. So what's the integral from 0 to 6 of f of x dx? Again, we're going to look at the function. The function is it positive? Of course not. The function here, up to here, it's negative. And up to here, from here to here, it's positive. So I'll give you a minute to tell me what is the integral.
6.
6? Anybody agree? Anybody agree with 6? Anybody agree, yes or no?
Yes.
Yes? Okay. The area here is 2. What's the area of this piece?
8.
8, because it's a half times the base is 4, times the height, which is 4. 6, that's equal to 8. So the geometric interpretation of the integral tells me this is going to be equal to minus the area of the region below plus the area of the region above. This is going to be equal to 6. Okay, so the integral is geometrically, as long as the function is positive, is the area. If the sums start moving between negative and positive, is what we call the net area. That's the interpretation of the integral. I had one more example I was hoping to do, but I will do the first 2 questions, so get you ready for the homework. So, okay. Suppose I have the following example. I take the function f of x equals x squared minus x. And question number 1 is, remember that the integral is what happened to the Riemann sums when n is a lot. So suppose I ask you to estimate the integral from 0 to 2 of x squared minus x dx using 6 subdivision and write Riemann sum. With 6 subdivisions. Okay, so I'm going to estimate the integral using 6 subdivisions. So the first step is always sketch the graph of the function. And over which interval I need to sketch the graph. 0 and 2. Tell me which interval I'm interested in. 0 and 2. So now let us sketch the graph of this function. X squared minus x, that's a parabola going down. It's nice to know the zeros of it. I said this equal to 0. I get x times x minus 1 equal to 0. So that's 0 here. And that's 0 at 1. And that's a parabola going down. So it's going to be like this. Okay. And need to estimate this integral using 6 subdivisions. So this is the easy part. We divide into pieces. And we evaluate the delta x. It's 2 minus 0 over 6. It is a third. Okay. So this is going to give me a third, 2/3, 1, 4/3, 5/3, and finally 3. So R6 is, now we know what it is 12 of 1/3 times delta x plus f of 2 times delta x. And we evaluate this, we get 1.037. Okay. And graphically, what does this represent? F of 1/3 delta x minus this area. F of 2/3 minus x, also minus this area. F of 1 is 0. So this is going to represent minus the sum of the area of both rectangle plus this. The problem. Okay. Question number B, and that's the last question, so you can do the homework carefully. I'm asking you, write the integral. Write the integral as limit of Riemann sum, because I want you to start seeing those sums. Limit of Riemann sum. What do I mean by that? It's very simple. So what I would like you to do is the following. That's what I mean by this question. Evaluating this integral, it means you have to take a sum. So basically in your mind, you take the interval 0, 2, and you chop it into n pieces, x1, x2, etc. And you take the following sum. You take the value of the function. The value of the function is xi squared minus xi. That's the value of the function. And what you multiply it by is the delta x, which is 2 over n. That's my delta x. And then you evaluate the sum from 1 to n. So this is the sum up to n. For the integral, what you do is you take the limit as n goes to infinity of the sum. So when I'm asking you to write the integral as limit of Riemann sum, I'm asking you to write it this way. The goal, as I repeat several times, we want to be able to recognize a Riemann sum when we see it. Okay. All right, I stop here. Do you guys have any questions? The homework will be on the place in 2 minutes. Do you have any questions before I let you go? Okay. Thank you very much and have a wonderful day. Bye, guys.
Bye, Professor Elias.
Bye, welcome. Thanks a lot, guys. Bye.